Nominal voltage represents the approximate or average voltage of a system or circuit when operating under normal conditions. It's typically used to identify the voltage class of equipment and components. It's important to remember that nominal voltage may not precisely match the actual voltage due to load variations and other factors. Rated voltage, on the other hand, is the specified voltage at which a device or system is designed to operate continuously. Insulation, conductors, and other components are designed and tested to withstand this voltage level. Exceeding the rated voltage can damage equipment or create safety hazards. System voltage refers to the actual voltage present in a system at a specific point in time. It's influenced by factors such as voltage drop along transmission lines, load variations, and voltage regulation. Consequently, the system voltage can fluctuate from the nominal voltage due to these influencing factors. So how do these three voltages relate to each other? The nominal voltage is generally close to the rated voltage, but it can be higher to compensate for voltage drop. The system voltage varies around the nominal voltage based on load and system conditions. Crucially, the rated voltage represents the operating limit, and the system voltage should not consistently exceed it. To illustrate this, consider a residential electrical system. It might have a nominal voltage of 120 volts. The circuit breaker and wiring might be rated for 125 volts to provide a safety margin. The actual voltage at a given circuit could vary from 120 volts to 124 volts at different times of day or under varying load conditions. Understanding these voltage differences is important for several reasons. Firstly, it's essential for selecting the equipment and components appropriate for the system voltage. Secondly, it's crucial for ensuring the safe operation of electrical systems by preventing excessive voltage stress. And thirdly, it helps in understanding the limitations and variations inherent in electrical systems. Voltage drop is a critical concept in understanding system voltage. As electricity flows through wires, some voltage is lost due to the wire's resistance. This voltage drop means that the voltage at the end of a long wire run will be lower than the voltage at the source. The amount of voltage drop depends on the wire's size, length, and the current flowing through it. Proper wire sizing is essential to minimize voltage drop and ensure that equipment receives the voltage it needs to operate correctly. Voltage regulation refers to the ability of a power system to maintain a stable voltage level under varying load conditions. Voltage regulators are devices that automatically adjust the voltage to compensate for changes in load. They are commonly used in power supplies, generators, and transmission systems. Good voltage regulation is essential for ensuring that equipment operates reliably and efficiently. In summary, the nominal voltage is a reference point, the rated voltage is a design limit, and the system voltage is the actual voltage you measure in a circuit. All three are intertwined, and understanding the differences between them is essential for safe and effective electrical work. When selecting equipment, always check the rated voltage to ensure it matches the system voltage. Avoid operating equipment above its rated voltage, as this can lead to damage and safety hazards. Regularly measure system voltage to identify potential problems such as excessive voltage drop or voltage fluctuations. By paying attention to these details, you can ensure the safe and reliable operation of electrical systems. Let's delve a bit deeper into the implications of exceeding the rated voltage. When electrical components are subjected to voltages higher than their rated values, several adverse effects can occur. Insulation breakdown is a primary concern. Insulation materials are designed to prevent current from flowing where it shouldn't. Excessive voltage can weaken or damage insulation, leading to short circuits and potential fires. Another consequence is component failure. Overvoltage can stress electronic components such as capacitors, resistors, and semiconductors beyond their design limits, causing them to fail prematurely. This can result in equipment malfunction and costly repairs. Safety hazards are also a major concern. Overvoltage can create a risk of electric shock, especially if insulation is compromised. It can also increase the likelihood of arcing, which can ignite flammable materials. Therefore, it is imperative to take precautions to prevent overvoltage conditions. Surge protection devices, or SPDs, are designed to protect equipment from voltage spikes caused by lightning strikes or power surges. SPD divert excess voltage to ground, preventing it from reaching sensitive components. Voltage regulators, as mentioned earlier, help maintain a stable voltage level, preventing fluctuations that could exceed the rated voltage of equipment. Proper grounding is also crucial. A good grounding system provides a low impedance path for fault currents, helping to prevent voltage buildup and reduce the risk of electric shock. Regular inspection and maintenance of electrical systems can help identify and address potential overvoltage issues before they cause problems. Look for signs of damaged insulation, loose connections, or corroded wiring. These conditions can increase the risk of overvoltage and other electrical hazards. Now let's consider some practical examples of how nominal, rated, and system voltages apply in different situations. In industrial settings, equipment such as motors, transformers, and control panels typically operate at higher voltages than residential systems. Common nominal voltages include 480 volts, 277 volts, and 208 volts. The rated voltage of this equipment is usually slightly higher than the nominal voltage to accommodate voltage fluctuations and provide a safety margin. The system voltage in an industrial plant can vary depending on the load and the performance of the power distribution system. Proper voltage regulation is essential to ensure that equipment operates reliably and efficiently. In data centers, maintaining stable voltage levels is critical for the reliable operation of servers, networking equipment, and other sensitive electronics. Data centers often use uninterruptible power supplies, or UPSs, to provide backup power and voltage regulation. UPS can automatically switch to battery power in the event of a power outage, ensuring that equipment continues to operate without interruption. The nominal voltage in a data center is typically 120 volts or 208 volts, and the rated voltage of equipment is designed to match. The system voltage is carefully monitored and regulated to prevent voltage fluctuations that could damage equipment or cause data loss. In renewable energy systems, such as solar and wind power installations, voltage regulation is particularly important due to the fluctuating nature of these energy sources. Solar panels and wind turbines generate electricity at varying voltages depending on weather conditions. Voltage regulators are used to stabilize the voltage before it is fed into the grid or used to power local loads. The nominal voltage of a renewable energy system depends on the size and type of installation. The rated voltage of equipment is chosen to match the nominal voltage, and the system voltage is carefully controlled to ensure safe and efficient operation. When working with electrical systems, it is essential to use appropriate test equipment to measure voltage levels and verify that they are within acceptable limits. Multimeters are versatile tools that can measure voltage, current, resistance, and other electrical parameters. Voltage testers are simple devices that can indicate the presence of voltage without providing a specific measurement. Insulation testers, also known as megameters, are used to measure the resistance of insulation materials. This helps identify insulation breakdown and prevent electrical hazards. Before working on any electrical circuit, it is crucial to de-energize the circuit and verify that it is de-energized using a voltage tester. Follow lockout/tagout procedures to prevent accidental re-energization of the circuit while you are working on it. Always wear appropriate personal protective equipment, or PPE, such as insulated gloves, safety glasses, and arc-rated clothing, when working with electrical systems. This will help protect you from electric shock, arc flash, and other electrical hazards. In conclusion, understanding the differences between nominal, rated, and system voltages is essential for anyone working with electrical systems. By paying attention to these voltage parameters, you can ensure the safe and reliable operation of equipment and prevent electrical hazard. Remember to always follow safe work practices and use appropriate test equipment and PPE when working with electricity. If you are not comfortable working with electrical systems, it is best to consult a qualified electrician. Electrical work can be dangerous, and it is important to have the knowledge and skills necessary to do it safely. And always remember to consult the National Electrical Code, or NEC, for specific requirements and guidelines related to electrical installations. The NEC is a comprehensive set of standards that provides detailed information on safe wiring practices, equipment installation, and other electrical safety topics. Let's explore some additional aspects related to voltage in electrical systems. Firstly, the concept of voltage drop becomes increasingly significant over longer distances. In such cases, the selection of appropriate conductor sizes is crucial to minimize voltage drop and ensure that equipment at the end of the circuit receives adequate voltage. The NEC provides tables and guidelines for calculating voltage drop and selecting the appropriate conductor size for a given application. Secondly, voltage imbalance can occur in three-phase systems when the voltages on the three phases are not equal. Voltage imbalance can cause overheating and premature failure of motors and other three-phase equipment. It is important to monitor voltage balance and take corrective action if excessive imbalance is detected. Thirdly, transient voltage surges, also known as voltage spikes, can occur due to lightning strikes, switching operations, or other disturbances in the electrical system. These surges can damage sensitive electronic equipment. Surge protection devices, or SPDs, are used to protect equipment from transient voltage surges by diverting the excess voltage to ground. Fourthly, the grounding system plays a critical role in maintaining safe voltage levels in electrical systems. A properly grounded system provides a low impedance path for fault currents, which helps to prevent voltage buildup and reduce the risk of electric shock. The NEC provides detailed requirements for grounding electrical systems. Fifthly, the use of power quality monitoring equipment can help identify and diagnose voltage-related problems in electrical systems. Power quality monitors can measure voltage levels, voltage fluctuations, voltage imbalance, and other power quality parameters. This information can be used to troubleshoot electrical problems and improve the performance of electrical systems. Sixthly, harmonics are distortions in the voltage or current waveform that can cause a variety of problems in electrical systems. Harmonics can cause overheating of transformers and conductors, malfunction of electronic equipment, and interference with communication systems. Harmonic filters are used to reduce harmonic distortion in electrical systems. Seventhly, the voltage rating of electrical equipment is typically marked on the equipment nameplate. It is important to verify that the voltage rating of the equipment matches the system voltage before connecting the equipment to the electrical system. Eighthly, the NEC requires that electrical equipment be installed in accordance with its listing and labeling. This means that the equipment must be installed in the manner specified by the manufacturer and in accordance with the requirements of the listing agency, such as underwriters' laboratories, or all. Ninthly, the use of adjustable speed drives, or AS, can improve the efficiency of motors and other electrical equipment. ASD allow the speed of the motor to be adjusted to match the load, which can reduce energy consumption and improve performance. However, ASD can also generate harmonics, which may require the use of harmonic filters. Tenthly, the voltage regulation of a power system is affected by the impedance of the transmission lines, transformers, and other components in the system. Reducing the impedance of the system can improve voltage regulation and reduce voltage drop. The NEC provides guidelines for calculating the impedance of electrical circuits. Let's elaborate further on the implications of harmonics in electrical systems. Harmonics are sinusoidal waveforms with frequencies that are integer multiples of the fundamental frequency of the power system, which is typically 60 Hz in the United States. Common sources of harmonics include nonlinear loads such as electronic devices, computers, fluorescent lighting, and variable frequency drives. Harmonics can cause a variety of problems in electrical systems, including increased current flow in neutral conductors, overheating of transformers and conductors, malfunction of electronic equipment, and interference with communication systems. The total harmonic distortion, or THD, is a measure of the amount of harmonic distortion present in a voltage or current waveform. High levels of THD can indicate that there are significant harmonic problems in the electrical system. Harmonic filters are used to reduce harmonic distortion by blocking or diverting harmonic currents. There are several types of harmonic filters, including passive filters, active filters, and hybrid filters. Passive filters consist of inductors, capacitors, and resistors that are tuned to specific harmonic frequencies. Active filters use electronic components to generate harmonic currents that cancel out the harmonic currents produced by nonlinear loads. Hybrid filters combine passive and active filter technologies. The selection of the appropriate type of harmonic filter depends on the specific characteristics of the electrical system and the types of harmonic loads present. Power quality monitoring equipment can be used to measure harmonic levels and identify harmonic sources in electrical systems. This information can be used to design and implement effective harmonic mitigation strategies. In addition to harmonics, other power quality problems can also affect voltage levels in electrical systems. These problems include voltage sags, voltage swells, and voltage transients. Voltage sags are temporary reductions in voltage that can cause equipment to malfunction or shut down. Voltage swells are temporary increases in voltage that can damage sensitive electronic equipment. Voltage transients are short-duration, high-voltage spikes that can also damage equipment. Power conditioning equipment, such as voltage regulators, surge suppressors, and uninterruptible power supplies, can be used to protect equipment from these power quality problems. Voltage regulators maintain a stable voltage level despite fluctuations in the incoming power supply. Surge suppressors protect equipment from voltage transients by diverting the excess voltage to ground. Uninterruptible power supplies provide backup power in the event of a power outage, ensuring that equipment continues to operate without interruption. When selecting power conditioning equipment, it is important to consider the specific power quality problems that are present in the electrical system and the sensitivity of the equipment being protected. It is also important to ensure that the power conditioning equipment is properly sized for the load it is serving. Let's discuss the importance of proper grounding in electrical systems in greater detail. Grounding is the intentional connection of electrical circuits and equipment to the earth. The purpose of grounding is to provide a low impedance path for fault currents, which helps to prevent voltage buildup and reduce the risk of electric shock. There are two main types of grounding systems: service grounding and equipment grounding. Service grounding is the grounding of the neutral conductor at the service entrance. Equipment grounding is the grounding of the non-current carrying metal parts of electrical equipment, such as enclosures and conduit. The NEC provides detailed requirements for grounding electrical systems, including the size and type of grounding conductors, the location of grounding electrodes, and the methods for connecting grounding conductors to equipment. A properly grounded system provides several benefits. Firstly, it reduces the risk of electric shock by providing a low impedance path for fault currents. This allows the fault current to quickly trip a circuit breaker or fuse, de-energizing this circuit and preventing a dangerous voltage buildup. Secondly, it helps to prevent voltage buildup on non-current carrying metal parts of equipment. This reduces the risk of electric shock if a person comes into contact with the equipment while it is energized. Thirdly, it provides a stable reference point for voltage measurements. This makes it easier to troubleshoot electrical problems and ensure that the equipment is operating properly. Fourthly, it helps to reduce the effects of electromagnetic interference, or EMI, on sensitive electronic equipment. EMI can cause equipment to malfunction or produce inaccurate readings. Regular inspection and maintenance of grounding systems are essential to ensure that they are functioning properly. Check for loose connections, corroded conductors, and damaged grounding electrodes. Test the resistance of the grounding system to ensure that it is within acceptable limits.